We've seen the comparison test that we can use to compare two improper integrals to see if potentially one converges or diverges, knowing that the other does. And this is actually going to be the same idea. Instead, though, we're going to use a comparison to compare two series. So our setup here is we're going to assume both of our series have positive terms, or I should say non-negative terms. Let's call those terms a sub k and b sub k. And we'll also assume that we know for all k that a sub k is less than or equal to b sub k. Then in that case, there are going to be two possible useful conclusions. If we happen to know that the sum of a sub k, the smaller sum, diverges, then it must be true that the sum of b sub k diverges as well. On the other hand, if we know that the sum of b sub k, the larger sum, converges, then the sum of a sub k must converge also. And we can think about this again by considering whether or not the sum is finite. So if I know that my smaller sum is infinite, that's going to force the larger one to be that as well. That's kind of the first idea here. And in the second case, if I know that my larger sum is finite, then my smaller sum must be as well. Notice that there are two other possibilities which just happen to be inconclusive in this instance. If you happen to show that the smaller sum converges, or if you show that the larger sum diverges, then we won't be able to conclude anything using the comparison test. So that's the idea behind it. Part of what's difficult is knowing what to compare to. Also, of course, when do I use the comparison test? I'll say in general, my instinct is to use the comparison test if I ever encounter a series that looks almost like a p-series or almost like a geometric series. And I'll look at this first example here. And this is an instance where both of those statements really hold true. So I'm going to focus on the fact that within here, I see the sum of 1 over 2 to the k, which is geometric. But I also see the sum of 1 over k, which is a p-series. P-series and geometric series are really nice to use for the comparison test because we can quickly decide if those series converge or diverge. Using the comparison test is going to be complicated if we have to do a lot of work even to check whether the one that we're comparing to converges or diverges. So it's not immediately obvious which, if either of these known kind of comparisons, will actually be useful. So let's look at them one by one. So my first thought here is to look at the sum from k equals 1 to infinity that we are given and try to think about how I might be able to compare that to the sum of simply just 1 over 2 to the k. So first of all, notice that the denominator of what I've written on the left is larger. K is always positive. So consequently, the inequality will face this way. If I do the same, where I instead compare my original series to 1 over k, the sum of that, the same inequality holds true here because, again, my denominator on the left is larger. So both things that I circled there really provide us with something larger than what we started with. Now, to use the comparison test, now I need to know what I can say about these two different upper bounds. Noticing that this first one, you can write that as 1/2 to the k, I can see that's geometric. And in particular, I can right away say that this converges, and you'd want to justify that. And so the way I can do so is to say that this is geometric. And recall that as soon as you have a geometric series, you need only look at the absolute value of r. In this case, that's 1/2, which is certainly strictly less than 1. However, for the second bullet point here, the comparison series diverges. And again, I can quickly justify that by pointing out that it's a p-series where the p-value it's equal to 1, but in particular it falls into the category of less than or equal to 1, and we know that p-series diverge in that case. So everything we've written so far is true. It's just that we have to decide which, if either, is going to be useful. And turns out that the useful one, let me pick a different color, is the first bullet. So knowing in our second bullet there that our series is bounded above by a diverging series just gives us no information. So it wasn't problematic to write it down, but just to note that it's not going to help us in this instance. So we're going to be able to say that the given series converges by the comparison test. So again, you want to get into the habit of always indicating what test you're using. And then on top of that, we need to show work. And in this case, the work was by identifying what the comparison series is and how we know whether it converges or diverges. So another example here, when I look at this, in this one, this series really just looks almost like a p-series. There's not an actual kind of geometric series in there. So my first instinct is to draw out that p-series I see, which is the sum of 1 over k squared. In this instance, again, we can see that's larger than what we started with. Our denominator was bigger. And we know that this p-series converges because p is equal to 2, which is strictly greater than 1. So in this instance, again, we're going to be able to quickly conclude that the series we started with converges, and we want to say by the comparison test. Now in this third one, there are two kind of, again, natural series that I might look to compare. One is k over k squared, and the other is 1 over k squared. Now, in general, to get the best comparison, so to get something that is going to be most representative of the behavior here, when you have, for rational expressions, what I'll say, when using the comparison test, choose the highest exponent in the top, in the numerator I should say, and the highest in the denominator. Okay, so what do I mean by that? Here there's not a lot of choice, but just to kind of look at this, if we had something of the form k squared plus k plus 1 over k cubed plus 2, something like this. If I wanted to think about the most reasonable thing to compare to, what I'm going to focus on is the biggest exponent in the top and the biggest in the bottom. And effectively then, the series I would want to compare to would be the one that just draws those out, which we would be able to simplify to 1 over k. So that's kind of the idea I'm expressing in red here. So you can imagine you could have a very complicated polynomial on top and bottom. Now, in our example, it's simpler in that I really only have, well, first of all, the highest exponent in the bottom is 2. It's the only one. But that tells me that I really want to go with what I've circled in blue, because the highest exponent in the top is 1. So I'm going to take my series and compare it to the sum of k over k squared, which is the same thing as the sum of 1 over k. Our series is larger because our numerator was larger, and we know that this series we're comparing to diverges. Again, it's a p-series with the p-value less than or equal to 1. So now we've bounded our series below by something known to diverge, so the series we started with must also diverge. And again, I want to justify that by saying that this is through using the comparison test. So sometimes what we'll see is we find a comparison by looking at all of our kind of hints here about what would make the most sense, but maybe the inequality doesn't face the way we would need it to. So for instance, if I had tweaked this problem just a tiny bit by making this a minus sign, then all of a sudden this inequality wouldn't go the right way. In that instance, I still want to take advantage of the fact that this really looks like a p-series, but it turns out that's going to be exactly the time where we'd want to use what's called the limit comparison test, which I'll discuss in another video.